Afternoon, everyone. Welcome to the Minalogic Business Meeting Conferences. My name is Bastien, and I will be your host today. First, please let me go through basic rules. So this is a recorded presentation. You will also be able to access the slides and all the contact information. Also, this is a 30 minutes presentation. We will keep the question to the end. So to ask any question, please click on the icon top right. You have two icons. You have chat and you have questions. Chat is for any logistics, any question, generic question you might have, and the specific question to Mr. Chris Meadows, it's in this specific icon. So top right questions. So I'm delighted to introduce you to Chris Meadows. Sorry for my spelling. The Director of CSconnected. This is the world's first compound semiconductor cluster in Wales, UK. Mr. Meadows will introduce us to the topic securing supply chain through collaboration, on building regional collaborative manufacturing capabilities, on new and emerging technologies. For now, no more spoilers. Mr. Chris Meadows, please, the floor is yours. Thank you.
Thank you very much, and thank you for the opportunity to talk a little bit about what we are doing in the UK in terms of the world's first compound semiconductor collaboration, if you like, and also the impact on where we are with a very global industry and what we're trying to do to make sure that we bring in sovereign capability and some homegrown capabilities that are based in and around Wales in the UK in general, and across Europe, to make sure that we have capabilities that are not totally dependent upon the US and Asia. Of course, working in semiconductors, there has been a lot of publicity over the last few weeks about shortages in semiconductors, and that really demonstrates how vulnerable we are as a nation and as a continent to global supply chains that are very fragmented and actually not necessarily that well understood, and how issues such as trade conflicts between the US and China, between Korea and Japan, and between Taiwan and China can have a major impact on the supply chains and the routes. Add to that the perfect storm of COVID and other changes happening in the supply chain, and suddenly we realize that we're all pretty vulnerable. I just wanted to go back a little bit and talk about some of the design to production processes, because although we are a fast-moving industry, actually the time involved in bringing a product to market can actually be quite long. And I like the American futurist, Ray Amara, who his comment about we tend to overestimate the effect of a technology in the short run, but underestimate the effect in the long run. And I'm guilty, and I'm sure we're all guilty of that. If you work in technology, you actually think that things are moving much more quickly than perhaps they are. It's only when you look back and realize actually it was quite quick. For example, automotive vehicles, driverless cars. We've been talking about it for some time, and we keep thinking it's just around the corner, it's just around the corner, because we're anticipating it and we think it's really very close. But actually there are there's a reluctance upon the population to jump into a totally automated car. And so it actually comes to us in stealth. For example, we're gradually moving towards automated vehicles with parking sensors, park assist, and automatic lane driving. So eventually, it's going to be a relatively small step to go to an automatic and driverless vehicle. But we don't spot it when we're running up to that point. However, when we look back in history, we'll think that it was actually a very short space of time. And if you look at products such as tablets and smartphones, again, the development of new technologies in that field, when you're working on those technologies, you really anticipate a very quick take-up. but in practice, it always takes a little longer than we thought. Yet when you look back, it feels as if it's always been with us. And I sometimes have to remind myself that even the first smartphone, the Apple smartphone, only came out in 2007, 2008. Tablets such as the iPad and other tablets. And and the innovation period, which is actually where the highest cost comes in, is a really important factor, because the companies and the countries that own the IP tend to be those where the major products are either produced or the revenues are achieved. So unless you own the IP, you don't really own the product. And the UK, and in particular Wales, has a history of inward investment, reliance upon investment from overseas, particularly North America and the Far East. But of course, the IP does not reside within Wales, it resides at the home nation, and therefore it's quite vulnerable in terms of when a company, perhaps that organization tends to retrench and go back home. So a total reliance upon foreign direct investment can be make you quite vulnerable. This chart I found quite interesting because it shows the development period for a range of technologies over the last century or so. And you can see that the general time that it takes to develop and bring a product to market is actually almost as long as the time that you have to generate revenues from that product before it becomes a mass commercial product, which brings in a lot of competitors, and you then share the field. When we talk about speed of adoption, I find it quite interesting that that's where things really have moved very quickly. And if you look at the adoption of the telephone, for example, to reach a mass market of 50 million users, it took around 50 years. If you look now at the television, that was 22 years. You come down to mobile phones, took only 12 years. But now, if we look at software applications, we're talking a matter of days. And actually, I understand that more recently, products such as, I think it was Pokemon Go, or some of the Facebook applications, actually are within a day. So we're starting to measure things within hours. So this gives the impression that we are a very fast-moving industry. And within a lot of the developments that we see, it is very fast-moving. The technology is moving very quickly. And I think one of the considerations we need to look at is the development cycle. And this is where collaboration really comes in as a strength. And European projects such as Horizon, and also within the UK, we have Innovate UK programs. They tend to concentrate on TRLs 4, 5, and 6. The TRL scale was developed by NASA back in the 1960s, where technology readiness level 1 is effectively John Kennedy saying that we will send a man to the moon and return him safely. And then at the end of the decade, Neil Armstrong going to the moon and coming back safely, which would be TRL 9. Between all of those stages, you've got all of the blue sky research that leads up to something that's patentable. So when you get to technology readiness level 3, you can patent it. 4, 5, and 6 is really critical in terms of bringing products to market. And it's really the innovation stage and prototyping. And then 7, 8, and 9 is really commercializing and actually gaining revenues. Interestingly, historically, the UK and Europe and North America, to a lesser extent, have really focused on TRLs 1, 2, and 3. So we're very good at developing the IP, the intellectual property. What we've not been so good at through history is in developing those products further and those designs in order to commercialize them. Some of that is down to funding, and across Europe, things like state aid rules have made it difficult to invest beyond TRL 4, 5, and 6. Similar in North America, in order to prevent competition between the different states in North America, a lot of the focus has been on funding 1, 2, and 3 rather than the late end. What's quite interesting is that China and other Asian nations have actually concentrated on technology readiness levels 7, 8, and 9, which means that they've had real focus on commercializing products that actually have been developed elsewhere. So that's set up what's really been an unlevel playing field over many years. But I think we're now starting to see a change in this trend. Certainly across Europe, a program called IPCEI, the Important Projects of Common European Interest, was developed and was really there around industries such as microelectronics to make sure that investment in higher TRLs could be made without contravening state aid rules. So it was basically a waiver. And there are similar programs across North America to achieve the same ends. So it's a recognition that we need to be able to develop the products and the IP that we develop in our nations to protect where the cash, if you like, or the revenues are made from our developments. Just stepping back a little bit in time, this is actually me a few years ago, and I have to say several years ago. My hobby was at one point, about 20 to 25 years ago, flying. And I was actually really proud to have one of the very early GPS systems. A handy little device with a very small LCD screen. And although it was never used for primary navigation, it was quite a breakthrough because when you go back to these vintage airplanes, when they were first designed and manufactured, a lot of towns and villages had railway stations, and the name of the railway station was on the roof of the station building. So you could actually navigate from one town to another just by reading the name of the towns. Of course, we don't do that anymore. And so using GPS and other navigation aids is really great. And we've obviously seen that evolve over the years. But I'm always reminded that initially the whole of the GPS satellite network was owned by North America. They launched the satellites, they owned the satellites. And I was actually in a position where I wasn't relying on it, but it was a helpful tool to tell me where I was. And suddenly it went wrong. It went to due north. And it turns out that North America, during the Gulf War, or the run-up to the Gulf War, actually switched off access to the satellites. They encrypted the satellite signals so that only the US military could use it. And it's always occurred to me that if one nation can control something as fundamental as GPS, that's actually quite a dangerous position. And now, if you think about how reliant we are upon systems such as GPS and global systems, then obviously it hits home a lot more, particularly as we move into driverless vehicles that will rely on these sort of technologies a lot more. Now, fortunately, with the satellite navigation systems, these are now pretty much globally owned and shared. And so we have less vulnerability. But that was quite an early stage at how vulnerable we can be when we are subject to a technology that's primarily dominated by one nation. And of course, in the last 2 or 3 years, we've been through similar examples, particularly with investment of overseas Asian organizations in telecoms networks. And of course, North America, Europe, and the UK are trying to mitigate the vulnerability by not allowing certain companies such as Huawei to be in the essential infrastructure of the communication systems. So these things keep happening. There is also, if you look at power electronics such as gallium nitride, silicon carbide, which are the fundamental materials for electric vehicles, The dominant company for that is a company called Cree, which is based in North America. And if we look at the example that happened between Donald Trump's regime and China, we can see how easy it is to cut off the supply of a particular product. And so these vulnerabilities continue. And we can see the impact that starts to have on supply chains that does affect us all. So there is a need to be able to make sure that we have the capability to at least develop the IP and then own the process within regions such as Europe. North America is doing the same. China is doing the same to protect itself from its vulnerability and dependency on chip supply from North America. And Korea has also announced a major investment to make sure that it can beef up its capabilities. So it's a real hot topic at the moment. And just going into the semiconductor revolution, if you look at how quickly it has developed, just reminding or reminder of the fast-moving market that we're in. The developments since 1971 are pretty tremendous, going from the first Intel chip with 2,500 transistors combined on a single chip to more than 23 billion transistors on the latest generations of products. So these are not minor increments, these are major developments that have happened over time. And so you need to make sure you have IP in each of these areas in order to keep up. And we've really seen the revolution in communications, in digitization, and soon quantum as really being dependent upon materials. And I kind of like it to look at it as three different phases, where we had the analog phase, we moved to digital, but of course we're analog people, we're analog beings. And so quantum is really a complex way of combining digital and analog, because it then takes out the digitization, the quantization, if you like, of data and the way that we work. And so we will continue to see a lot of developments that are all based on materials technologies. And I often look back and think evolution itself has been defined by the materials that have dominated a particular age. So, for example, we started off with the Iron Age, or the Stone Age, the Bronze Age, the Iron Age. And I do wonder if over the last century or so, future generations will look back on this being the steel age, the plastic age, or possibly the semiconductor age. But it's all about the materials that dominate a particular era. And from a CS-connected point of view, CS is compound semiconductors. Obviously, silicon has dominated the industry during the analog age and has really ushered in the digital age over the last 50 years or so, and will continue because it's commoditized, it's easy to find the raw materials, and it can meet the majority of needs. But where you need very high performance or optical properties, then we need to start combining at the atomic level different materials. And this is where compound semiconductors comes in. And so combining indium, phosphorus, gallium, arsenic, nitrogen, and so on, along with silicon, we can achieve properties of next generation devices that far exceed current technologies with silicon. So I think ultimately the two technologies will come together. But as I said earlier, the supply chains for these products are very fragmented. So if you take the semiconductor materials, they go through several stages, and it may be 10 or 15 different stages in the supply chain before it ends up in the final application, whether that's electric vehicles, 5G communication systems, energy systems, robotics, and so on. So quite often we lose sight of the detail of those supply chains, and we've seen the impact historically of, for example, the tsunami back in, I think it's 2006, on the whole of the supply chain. And a lot of that was actually not on the direct supply chain, but it was on, or one of the key factors was a factory in Japan that was producing the epoxy resin that was used as part of the packaging of silicon onto the packaging systems. And so there are lots of vulnerabilities that are not necessarily known across the whole of the supply chain structure. And when we look at things like telecommunications, in the UK, for example, British Telecom Labs was one of the key pioneers in broadband technology. And interestingly, from the UK, even today, a lot of the products for laser communications and fiber optics are exported from the UK to Asia, to Taiwan, Korea, Japan, for example, and North America. From there, they quite often end up back into China to companies like ZTE and Huawei, who then export from China and are imported back into systems. Ironically, companies like BT being the end customers. Although it's interesting that each stage in the supply chain can be an order of magnitude higher in value than the previous stage. So $10 million worth of product shipped from the UK translates to almost $10 billion of imports by the time the value has been added at different parts of the supply chain. And of course, we then have these vulnerabilities of global shifts, whether it's geopolitical, it could be natural disaster, or I guess included in natural disasters, pandemics that affect the different parts of the supply chain. When we look at our industry, the semiconductor industry, it has traditionally been evolved in clusters, starting with Silicon Valley in California, but also Korea, Japan, and more recently Taiwan. And in fact, a lot of what was happening in Silicon Valley has now migrated to Taiwan. And so the largest chip company in the world is TSMC, and effectively has taken over where the likes of Intel were many years ago. But across Europe, we have four real strength in clusters. Obviously, Grenoble being one of those, but around ST Microelectronics, there's always an anchor company or some core at the center of a cluster. In Leuven, in Belgium, that's centered around IMEC. In Eindhoven, we have Philips. In Dresden, around Infineon, Siemens. And those really are key clusters, with around 800 key companies in total, employing 150,000 people. And these are real European centers of expertise. So we already have the core of manufacturing capability. It may not be quite at the scale that we had in Silicon Valley and in Taiwan now, but it's certainly a force to be reckoned with. So we have the base capabilities already. And in the UK, we now have what we think will be the fifth cluster, semiconductor cluster, but certainly the first focused on compound semiconductors. And that's really across a number of companies, businesses, and supported by the Welsh Government and an organisation called the Cardiff Capital Region, but ranges from the TRL 1, 2 and 3 at the universities such as Swansea and Cardiff University, all the way through to high volume manufacturing with an organisation called the CSC and another one called the CSA Catapult, who concentrate on TRLs 4, 5 and 6 within the cluster. And when we talk about clusters, quite often a cluster is just a random collection of organizations that have something in common. They may use a common customer base, but quite often they're competing. Within the cluster in South Wales, this is quite unique in that we found that although most of the companies and activities have been around for about 30 years, it's only over the last 5 or 6 years that we've really started working together so that we actually have an internal supply chain that we've managed and developed over time. And some of that came about because we discovered that some companies in the cluster were shipping products to Taiwan and North America, and then those companies were shipping them back to the region for further processing. So we started working together, and rather than calling it a cluster, I like to call it an ecosystem or a community, because we do collaborate very strongly across the TRL levels, so all the way from pure concept right through to volume manufacturing. But also we are now starting to develop some of the vertical supply chains, which is helping to bring some of the technologies back to Europe, UK, and in particular to Wales. And that's come about through a number of investments, which we believe is very close to $1 billion public and private commitment over the last 5 years, and committed over the next 5 years. We really are seeing the fruits of a lot of this collaboration that's been happening. And if you look at many clusters, there's not so much collaborative activity that's happening within them, except that there may be several relationships between perhaps a university and several of the organizations. So what we think we have in Wales is very much this unique infrastructure. And as I said, organizations such as Cardiff University, Swansea University, where we're developing these major wafer fabs for research, development and innovation, really covered TRLs 1 all the way through to 9, with the Compound Semiconductor Centre and the UK government Catapult, which is very similar to Fraunhofer, which is focusing on the innovation and prototyping of applications for compound semiconductors. So across the whole gamut, we actually have quite a wide range and a holistic profile. And some of this has come about through what's called the Levelling Up Agenda in the UK, where the aim is to reach an investment of 2.4% of the gross domestic product by 2027 being spent on research and development. Because, as I said earlier, unless you own the IP, you don't really own the whole of the product line. So that's really a key ambition of the UK government. And as part of that, companies and other organizations within the current cluster are actively working on a number of collaborative research and development programs. And you'll see at the bottom the list of names from Newport Wafer Fab, CSC, Microchip, SPTS, and IQE are collaborating together and with universities and the Catapult and CSC on a number of discrete projects that we would hope to exploit and develop both an internal market for, but also an export market, so that we're contributing to the global supply chains, but that we're also developing technologies and supply chains that are less dependent upon overseas imports, particularly from North America and Asia. And I think this is a model that certainly can be replicated. So we're quite excited about the possibilities that come from these collaborative research and development programs, and also the role that the cluster can play in reshoring some of the technologies that ironically were developed initially in the UK and across Europe, using Innovate UK and its predecessors, and also Horizon 2020 and hopefully in the future Horizon programs. So very much a whistle-stop tour. I hope it's all made sense, but we believe that sovereign capability is really important. In the last 2 or 3 months alone, on the back of the semiconductor shortages, we've seen Joe Biden holding a wafer in his hands, saying that they're committing $50 billion in developing further and strengthening their semiconductor businesses. In Europe, Ursula von der Leyen has committed $145 billion by 2030, and Korea $450 billion. and China has topped that with a commitment to expand its semiconductor capabilities by $1 trillion over the next 10 years to reduce its dependency on North America, as I said. So hopefully that all makes sense, and happy to take any questions.
It was great, Chris. Thank you for sharing your knowledge and perspective on this. First, we have a question asking about the manufacturing core in Europe. What do you think is missing in order to achieve self-sufficiency?
I think we have all the components. The main thing that's missing is scale in some of the new areas. So we do have, as I mentioned, 4 large manufacturing clusters across Europe, with Wales being the 5th one. I think it's largely down to investment, which again, I know through programs such as IPSI is changing, but actually we've got all the components of the supply chain. And by encouraging what I think we've done in Wales, the collaboration, so that we can make sure that we've got close connections between TRLs 1, 2, and 3, all the way through to the end of that horizontal development chain, I think is a real strength that we can build on. So I think we have the capability. What is needed is investment, and clearly that's been seen with a commitment of up to $150 billion over the next euros over the next 10 years.
It was great to listen to you. I mean, from the lesson learned on how we can improve from learning from our past and how we can overcome those challenges on semiconductors. We have a second question. It is, how can you secure that European SC facilities will be used by industry?
So, sorry, could you say
how can you secure that European SC facilities will be used by industry?
I'd like to quote the phrase "build it and they will come." I think it's about the sovereign capability, and I think the vulnerability. In some ways, it may be a positive outcome of the current shortages that the automotive industry and the consumer industry are seeing, in that there are some long timescales within the semiconductor industry in qualifying new products and processes. And what we've seen over the last year with trade wars and with COVID is that we've had to move a number of these supply chains. And the biggest issue is in re-qualifying the new supply chains, even though they use many of the same components. And so I think by understanding, and actually government involvement in understanding the importance of the industry, raising the profile, I think will help create startups, spin-outs from universities. But actually, although I said we shouldn't be dependent on foreign direct investment, I don't think there's any harm in attracting in additional foreign direct investment within the supply chains, as long as it's to contribute to the region rather than just to acquire the IP and then take it to North America or Asia or whatever to manufacture. I think we just need to have the confidence in ourselves to make sure that we can do that and maintain it.
Well, you know, Minalogic as a cluster, we also believe that collective intelligence make us stronger. And I have maybe one question for you. How do you foresee, how do you believe we could achieve from a pan-European collaboration, how we can achieve this collaboration between us from different countries?
I think I sometimes use one of the supply chains. I'd use an example. We've seen it with COVID and with the vaccine process, in that a lot of the sciences and technologies tend to be very collaborative. And although at the political level there may be some territorialism, shall we say, to try to protect, I think as scientists and technicians or technologists, we tend to communicate anyway, regardless of borders, regardless of what's happening in the geopolitical world. And despite Brexit, we continue to work with universities and institutes across Europe. And I think it's just a natural trend. You know, if you look at papers that are published, they're quite often collaborative anyway. And it's making sure that we can continue that through the TRL chain, but also through vertical supply chains. I think we're already good at that. We just need that to be recognized and to raise the profile.
Thank you very much for your optimism, which I would believe we share.
Thank you.
I believe that's all. No more questions for now. So, Chris, thank you very much.
You're welcome.
Have a nice day on MBM. Thank you.
You too. Thank you very much. Thank you. Bye-bye.